Okay, for the last question of the tutorial, we're going to take a look at the final exam of semester 1 2018-2019, which is 2 years ago. And this question actually covers all on induction motors and has a lot of analysis, so it's good to go through the rest of the question. The first part is that it asks under a normal load, the motor runs very close to synchronous speed, we know that. And if a 5 horsepower 6-pole induction motor is excited by a 3-phase 60 hertz source, what is the approximate full load speed that can be expected is basically we need to make sure that we know the amount of slip. Okay, so for small motors, 10 kilowatt or less, the slip is can be approximated at 5%, and this is in the book and in the lecture notes. Okay, so basically first we must find out how much is the synchronous speed first. Okay, so so the synchronous speed is simply 120 times the electrical frequency divided by pole, which is 120 times 60 over 6 will give you 1200 RPM. Okay, so if you take a look at this is a 5 horsepower, so we're looking at a 5 horsepower times 746 watt per horsepower, and we're looking approximately at 4 kilowatt motors. Okay, so this is a small one, so the slip can be approximated at 5%. Okay, so then therefore the speed of the motor is 1 minus s times the synchronous speed, which is basically 1 minus 0.05 times 1200 RPM lah. Okay, so this will give you 1140 RPM. Okay, so the knowledge of slip is approximately 5% will give you 1 mark. The equation will give you 1 mark, and then the correct answer will give you 1 mark, and this is 3 marks. Okay, so on the second part, it asks for the analysis. Okay, this question has actually a correction in the final exam, that the input power is actually is not given. So I have given the input power as a correction to be 10 kilowatt. Okay, so this is the active input power that was given to the motor. Okay, so if the same motor that has an input power of 10 kilowatt, the stator amounts to the stator losses is amounts to 500 watt, and the motor runs at 1152 RPM. Calculate the active power. Okay, so active power transmitted to the rotor refers to the air gap power. If we take a look at the power flow, okay, we know that we have output power, obviously, then input power, and for induction you have the air gap power here, and then you have the converted power. Okay, so in the case of air gap power, this side is the stator side, okay, and this side is the rotor side. Okay, so the active power that is actually transmitted, so active power means P lah, so it is transmitted to the rotor is obviously the air gap power, because this is the rotor side. All right, so we have losses at this point, the stator copper losses and the core losses. Okay, so it's not given the amount of core losses, so we can assume that it's 0 here. So we can find out the air gap power as the input power minus stator copper losses minus core, which is 0 here. So the input is 10 kilowatt minus stator copper losses is 0.5, so we have 9.5 kilowatt. Okay, now how much is the rotor losses? Okay, so the rotor losses is, okay, rotor losses means the rotor copper losses. This is A, B. The rotor copper losses, RCL, is basically the slip times the air gap power. So the slip can be found by subtracting the synchronous speed with the motor speed divided by synchronous speed, and we know synchronous speed is 1200. So minus 1152 divided by 1200 will give you 0.04. So this is a slip. So the rotor losses is the slip, the rotor copper losses is therefore the slip 0.04 times the air gap power, which is 9.5 kilowatt. This will give you 0.38 kilowatt. Okay, so this is the rotor losses. And then how much is the mechanical power developed? Okay, so the mechanical power is actually the converted power lah, because the converted power is T induced times omega m, right? So this is coming from the power flow diagram lah. Okay, so the converted power is the induced power times the motor speed. Okay, so this is the actual mechanical power developed by the machine. Okay, so P converted, if we look at the power flow, it is actually the P air gap, okay, minus P rotor copper losses. Okay, because in this power flow diagram, after the air gap, we will have losses. Okay, rotor copper losses before we have mechanical and the stray losses here. Okay. Alright, so the air gap power is 9.5 kilowatt, the rotor copper losses is 0.38, so this will give you 9.12 kilowatt. Okay, now the next part is the mechanical power delivered to the load. Okay, so delivered to the load means the output power lah. Okay, so the output power is obviously P converted minus whatever losses that we have here, which is the mechanical losses or the windage and friction losses. Okay, so it is given that if the windage, friction and stray losses amount to 0.2, the rest of that is 0.2 kilowatt. So that means the P converted minus 0.2 kilowatt. So we will have 9.12 kilowatt minus 0.2 kilowatt is 8.92 kilowatt. This is the output power or the mechanical power delivered to the load. Now, the last one is the efficiency. So, efficiency of the motor is obviously the output power divided by the input power times 100% lah. Okay. So, this is 8.92 divided by 10 times 100%. So, this will give you 89% efficiency. Okay. Alright. Last one is sketch a torque speed curve for the motor considering the conventional assumption that the nominal full load torque is T, starting torque is 1.5 T, and breakdown torque at 2.5 T. Okay, so we know that the nominal full load is T. Okay, so nominal full load is what? Okay, nominal full load, if you look at the notes, the lecture notes, the nominal full load is full load torque is the amount of we have to consider the amount of air gap power. So it's 9.55 times P air gap divided by the synchronous speed, which is 1200. So this is 75.6 Newton meter. So starting torque must be 1.5 times this torque. Okay, so it is 1.5 times 75.6 Newton meter, and this is 113.4 Newton meter. And then breakdown torque is 2.5 times this torque, which is 2.5 times 75.6, which is 189 Newton meter. And you need to sketch a torque speed curve. So basically, you just simply follow the graph of induction motor, and you need to plot lah here. So the starting torque must be 113.4, and then here must be 189, okay, Newton meter. This point must be 113.7. It must be labeled. So then therefore we know where the starting torque, where is the breakdown torque. And then the nominal full load torque we're looking at 75.6 lah. Okay, so we're looking at lower here 75.6. Okay, so this is the nominal full load torque. Alright. Okay, so this is how you get 5 marks. So basically, if you plot this, you get 3 marks. Okay, and this calculation is 1 mark and 1 mark lah. Okay, so that is the distribution of marks inside for this question. Okay, so therefore for induction motors, both for synchronous induction motors, it's important for you to understand the power flow. And if there is any of the power flow that was not given, okay, you can put your assumption. Sometimes people put stray losses, whether it's given or not, it is assumed at 1%. You can put it there because yes, it's true there are motors that are always at 1% stray losses. Sometimes it's 1.5, sometimes it's 2%, sometimes it's actually assumed 0. So all of the assumption must be put for you to calculate the output power. Okay, so as long as you know and understand the power flow diagram and how to actually execute that, I think there is no problem with the rest of the calculation.